Hi, I'm Shaopeng. I'm going to present our work in network pruning, named Differentiable Markov Channel Pruning for neural networks. Recently, some works viewed network pruning as a neural architecture search. Given an unpruned network, some works use reinforcement learning or other algorithms to search the pruned structures. The search space is usually the number of channels in each layer. And then the pruned structures are trained from scratch and get the pruned network. However, this optimization of these pruning methods need to train and evaluate a large number of structures and sampled from the unpruned network. The scalability is limited. The similar problem also exists in neural architecture search. A differentiable method was proposed to solve these kind of problems. For example, in the left figure, a layer has several candidate operations. Each operation has its corresponding probabilities. These probabilities are usually the categorical distribution. In the forward phase, the output is the sum of the products of all the output of operations with its probabilities. Finally, one operations are chosen among all the candidates by using the argmax operation. However, we cannot directly adopt this differentiable method in channel pruning. In pruning, instead of searching the operations, we want to search the number of channels in each layer. And this cannot be modeled by the categorical distribution. Therefore, we formulate the channel pruning as a sequence of transitions. For example, here is a layer with only 5 channels. State 1 means retaining the first channel, and state 2 means retaining the second channel, and vice versa. The terminal state T means the pruning process is over. The probabilities here is the learnable transition probabilities, which will be introduced later. These animations represent a pruning process. Finally, the rest of the channels are pruned. In the left graph, pk is defined to be the probabilities of retaining the kth channel given all k-1 channel is retained. And the first channel must be retained in our method. From the graph, we can easily conclude that the kth channel will never be retained given the k-1 channel is not retained. The left figure shows how to combine the learnable transitions with an unpruned layer. Alpha are a set of learnable parameters. Some works also call this the architecture parameters. The transition probabilities can be simply computed by a sigmoid function of alpha. With the transition probabilities, we can compute the marginal probabilities of each channel. By our definition, we can simply remove these terms because it equals to 0. Therefore, the marginal probabilities can be computed by the product of all previous pk's. Last, the final output of each channel is the product of all original output times its corresponding marginal probabilities. The training pipeline contains 2 stages. In stage 1, for each iteration, we sample several substructures from the transition model, and the compute gradient update weight of the unpruned network. In stage 2, we use the method mentioned above to combine the learnable probabilities with the unpruned layer, and then compute gradients and update the transition models. We performed this stage back and forth and finally got the optimized transition model. Using this model, we can get the pruned structure. Last, we show some experiments on Imagenet. Compared with baseline, MobileNetV2 has only 0.1 accuracy drop with a 90 megaflops reduction. On ResNet 50, There's no performance drop compared with baseline, with 1.3 gigaflops reduction. That's all for the presentations.